What lies within a black hole? It's a question scientists have pondered for over a century, and it remains unanswered. Should you cross an event horizon, everything you know about time, space, and reality itself would cease to function as expected. Today, we will attempt to peer into a realm no telescope has ever penetrated. First, I want to pose a question to you. How many numerical values would it take to fully describe the Moon, our closest celestial neighbor? Imagine its surface scarred by countless craters left by asteroids that have bombarded it for billions of years. Even if an exomoon strikingly similar to ours existed in a distant star system, its crater pattern would be entirely different, a unique cosmic fingerprint. To thoroughly describe each lunar crater, we would need at least two coordinates, longitude and latitude, to pinpoint its exact location, along with data about its size. Thus, describing thousands of craters would require thousands of numerical values. And that's just the beginning. We also need to consider the chemical composition of the lunar surface, which varies from region to region. In an instant, the number of required values skyrockets from thousands to millions, or even more. And this is merely to describe the Moon, one of the simplest objects in the cosmos. How many numerical values would be needed to describe an entire planet, a star, a nebula? Or, ultimately, how many numbers are necessary to describe the most massive object in the universe, a black hole? The answer to that question might seem incredible. Just three. Three numbers, and no more. Regardless of a black hole's mass or its birthplace, be it our Milky Way galaxy or an object billions of light years away, only three parameters are sufficient to define it completely. On one hand, this makes black holes astonishingly simple objects. Their classification requires only three characteristics: mass, electric charge, and angular momentum. Knowing these three numbers means we know everything about a black hole. And yet, there are countless ways for a black hole to form. They can grow gradually, accreting dust and gas over billions of years. They can arise from the direct collapse of a massive star in a Type II supernova explosion. Perhaps some grow by consuming other black holes. One could even imagine a hypothetical black hole formed from the content of every encyclopedia, every electronic database of all civilizations in the universe, every scrap of information, every number ever conceived or uttered. Anything in the universe can be swallowed by a black hole, but once it forms, all that information is reduced to those three numbers. How a black hole formed and what fell into it is practically irrelevant. A natural question arises. How is it possible that with such an incredible number of ways for a black hole to form, it can be described by just three numbers? Where does all the other information go? Does the black hole forget its origin, or is this information preserved in some hidden form? What is truly inside a black hole, and what might that mean for the rest of the universe? In the 1780s, the position of a parish priest in the Church of England was not particularly demanding. A large house with a good income, servants for household chores, and young curates to conduct services and visit the sick. For those who wished, it offered a life of idle leisure. But those who sought more had time for deep contemplation about the world around them. This is how the English clergyman John Michell spent his time. In the 1780s, Michell had a fairly good understanding of how gravity worked. A century earlier, Isaac Newton's theory of universal gravitation had shaken the scientific world. Newton argued that gravity is a universal force. Everything with mass attracts everything else, acting instantaneously. Nothing can escape the force of gravity, not even, as Michell pondered, light itself. Besides contemplating gravity, Newton also asserted that light consists of tiny, discrete particles, small atoms of light, which we now call photons. If this light as particles theory was correct and gravity was universal, then gravity must also act on these tiny particles of light, pulling them and holding them back. Michell also knew that light travels fast, very, very fast. The speed of light is truly phenomenal. It propagates with incredible rapidity. As early as the 18th century, astronomer James Bradley by analyzing the aberration of light from distant stars, managed to measure this speed with astonishing accuracy. Observing how the vectorial combination of Earth's velocity and the speed of light changed as our planet orbited, he noticed subtle yet sufficient alterations in the apparent positions of stars in the sky. Thus, the speed of light was determined to be approximately 180,000 miles per second. This was enormously fast, yet not infinite. Michel's intuition told him that any object thrown upwards would eventually fall back to Earth. But what if it were given enough acceleration? In that case, it could overcome Earth's gravitational pull and escape into space. The minimum speed required to overcome a planet's gravity and reach infinite space is called the escape velocity. Within Newton's theory of gravity, this speed can be easily calculated for any planet, determining its dependence on the object's size and density. The more massive and dense a celestial body, the higher its escape velocity will be. For the Moon, this speed is about 2.4 kilometers per second. For Earth, it's about 11.2 kilometers per second. For Jupiter, just under 60 kilometers per second. And for our Sun, approximately 617 kilometers per second. Now, let's imagine an even denser body. Michel wondered, what if there exists an object so dense that its escape velocity exceeds the speed of light? In such a case, light emitted from its surface would not be able to escape. This object would be a gravitationally massive yet absolutely dark body, trapping even light in its gravitational snare. Although the language and argumentation here rely on Newtonian physics, which was later revised by Einstein, the concept itself remains relevant and easily recognizable. Michel's work, though the term itself had not yet been coined, was the first description of what we today call a black hole. Michel's ideas were significantly ahead of their time, and his discovery was perceived as nothing more than an abstract curiosity. It was therefore shelved in the scientific long box for a full 150 years. This box was next opened in the horrifying trenches of World War I, where German astronomer Karl Schwarzschild, seeking refuge from the nightmare around him, immersed himself in contemplating the equations of Einstein's brand new theory of general relativity. After developing special relativity in 1905, Einstein successfully extended it 10 years later to include gravity, creating the general theory of relativity. This theory is described by 10 equations, which, though well known today, seemed formidable and practically insoluble at the time of their appearance. In 1915, the methods for solving these equations remained unknown. Schwarzschild, attempting to solve them, sought the simplest possible solution he could imagine: a spherically symmetric spacetime around a concentrated point mass. Carefully plugging in all the data and performing the calculations, he obtained a solution now known as the Schwarzschild solution, probably the most famous solution to Einstein's equations. The Schwarzschild solution includes one parameter: a uniform spherical mass. In general relativity, mass deforms nearby spacetime. The degree of this deformation depends on the radial coordinate. The closer to the mass, the stronger the deformation, while at greater distances, the changes are negligible. The Schwarzschild solution possesses one profound and astonishing property. As one approaches the mass from infinity, a critical distance arises where something strange happens. Some terms in the solution seemingly tend to zero, while others go to infinity. What does this mean? Although a complete mathematical derivation was not possible, these zeros and infinities at the critical radius, known as the Schwarzschild radius, indicated the existence of an event horizon for the black hole solution, a spherical shell at a certain distance from the black hole's center, which represents the point of no return for objects approaching from afar. No object in the universe can exceed the speed of light. Beyond the so-called event horizon, an object attempting to leave a black hole at the maximum possible speed theoretically has a chance to overcome the gravitational pull and escape to infinity. However, once in the immediate vicinity of a black hole, beyond the event horizon, even light has no chance of escape. The fundamental laws of physics preclude any possibility of escape. Any astronaut who crosses the event horizon is doomed to an unstoppable fall towards the black hole's center. Within this boundary, time itself relentlessly pulls towards the singularity. As one delves deeper into the black hole, the gravitational effect increases exponentially. Thus, the astronaut continues their descent until they reach the singularity, a point where the classical laws of general relativity cease to apply and the curvature of spacetime formally reaches an infinite value. This phenomenon echoes Michel's calculations about the radius at which escape velocity exceeds the speed of light. If a certain mass is compressed to a size smaller than its Schwarzschild radius, gravitational collapse is inevitable. The Schwarzschild radius for our Sun is approximately 3 kilometers, and for Earth, less than 1 centimeter. The Schwarzschild radius for a human is infinitesimally small, on the order of 10 to the 23, which is smaller than an atomic nucleus. Imagine that all the matter in the Milky Way, including stars, gas, and dust, was compressed to a radius of less than 2/10 of a light year. The result would be a colossal black hole, truly gigantic in size. Schwarzschild's equation was found in 1915, but like Michel's work, it was long considered merely a theoretical construct. It remained unclear whether it represented a physical reality or was just a mathematical curiosity. While quantum mechanics revolutionized various fields of physics in the 1920s, 30s, and 40s, gravity and general relativity remained in the shadows. The words of American physicist Richard Feynman about a gravity conference he attended in the early 1960s reflect the general attitude towards this field. "I got nothing useful out of that meeting. I didn't learn anything new. Because of the lack of experimental data, this field does not attract the best minds. Consequently, it is filled with mediocrities, which negatively affects my health." However, the state of affairs so critically described by Feynman changed dramatically in the late 1960s. A combination of theoretical breakthroughs and new observations breathed new life into the study of black holes and general relativity, both from theoretical and observational perspectives. This trend continues to this day. In the public consciousness, the name of one outstanding scientist is associated with this resurgence of space science, Stephen Hawking, who holds a special place among the prominent physicists of the 20th century. His astonishing biography has inspired millions worldwide. Born in 1942, he studied physics at Oxford University and then continued his education at Cambridge, working on his doctoral dissertation. During his dissertation work, Hawking's life underwent significant changes. First, at the age of 21, he was diagnosed with a degenerative motor neuron disease, for which the average life expectancy after diagnosis was about 18 months. Second, having graduated with a first-class honors degree from Oxford, he began to work with full dedication for the first time in his life. Realizing the threat of an early death, he fully committed himself to his work, striving to achieve significant results and leave his mark on science. Hawking lived much longer than expected with his diagnosis. He passed away in 2018 at the age of 76, being one of the most famous and respected scientists in the world. His scientific fame is linked to the period from 1967 to 1974, when Hawking's fruitful collaboration with mathematician Roger Penrose revolutionized the stagnant field of general relativity. The progress of general relativity owes much to the fruitful collaboration of Stephen Hawking and Roger Penrose, who jointly proved a series of fundamental theorems. Imagine a group of massive particles located in close proximity to each other and subjected to mutual gravitational attraction. Intuitively, it's difficult to predict their fate. A scenario where they collapse to form a black hole is possible, but their scattering in different directions is also not excluded. Hawking and Penrose brought clarity to this matter. They proved that under certain conditions, characteristic of matter, clumps undergoing gravitational compression, collapse is inevitable. The endpoint of this process is a singularity in space-time, surrounded by a black hole's event horizon. This conclusion was not based on intuitive assumptions or expectations, but represented a rigorous mathematical proof. The joint work of Hawking and Penrose also revolutionized relativists' understanding of space and time through the creation of a conceptual visualization tool known as Penrose diagrams. These diagrams significantly simplified the analysis of complex solutions to Einstein's equations. It became possible to obtain a clear and complete understanding of the causal relationships governing the behavior of black holes. Penrose diagrams allowed for a graphical representation of space-time structure, where light always traveled at a 45-degree angle, making it easier to identify regions that causally influenced each other. The event horizon could be interpreted as a boundary beyond which causal connections with external space cease. Despite his progressive physical decline, Hawking's mind continued to explore the expanses of space and time. There was growing evidence that the exotic objects described by mathematical formulas, black holes, indeed existed in our galaxy. In parallel with theoretical investigations, astronomical instrumentation developed rapidly. The launch of satellites with telescopes allowed for the first time to observe the sky beyond Earth's atmosphere, not only in the optical range but also in other spectra, including X-rays. The results of these observations were astonishing. The X-ray sky was far more active and vibrant than previously assumed. Among many sources, an especially bright and compact object stood out, named Cygnus X1. The nature of such intense X-ray emission remained a mystery. How could it originate from such a small volume of space? The only plausible explanation was the presence of a compact black hole, emitting energetic X-rays during the process of matter accretion. Since the identification of Cygnus X1 as a black hole in the 1970s, many similar objects have been discovered. It is estimated that there could be up to 100 million black holes in our galaxy. In 2015, the collision of black holes was first detected by the LIGO Observatory in the United States, which registered gravitational waves emitted during their merger. However, the excitement surrounding black holes during this period was not only driven by astrophysical observations. Theoretical research conducted in offices and laboratories became a new arena for studying the universe's most extreme phenomena. The human face is one of the most familiar objects to us. Despite shared features, it possesses an infinite variety of individual characteristics. Age, skin color, hair shade and style, freckles, moles, smile, teeth. A complete description of all these details would require an enormous amount of information. A black hole, in contrast, is a far less familiar and more exotic object, yet in some ways, it is much simpler. This simplicity is reflected in the solutions to Einstein's equations, although finding these solutions is not a trivial task. Soon after Carl Schwarzschild discovered the simplest solution describing a black hole in 1915, its generalization, the Reissner-Nordström solution, describing an electrically charged black hole, was found. The Reissner-Nordström solution added to the picture of the world, but the real breakthrough occurred in 1963, almost 50 years later. That's when New Zealand scientist Roy Kerr presented his solution, which became a crucial generalization of the Schwarzschild solution. Like the Schwarzschild solution, it described an uncharged black hole, but one that possessed angular momentum, meaning it was rotating around its axis. Imagine a giant ballerina spinning at immense speed and possessing colossal mass with her arms outstretched. This cosmic dancer is so massive that she is on the verge of becoming a black hole. When she pulls her arms in to increase her rotational speed, she crosses this critical density limit and instantly collapses, transforming into a black hole. But this is a rotating black hole, and the angular momentum she possessed before collapse does not disappear. It is transferred to the newly formed black hole, which is reflected in Kerr's solution. However, a question arises. Why are there so few solutions describing black holes? Besides the Schwarzschild and Kerr solutions, there are only their generalizations that account for electric charge. It turns out this limitation is not due to a lack of effort by scientists. By studying the equations of general relativity and analyzing what types of solutions lead to the formation of black holes, physicists concluded that these solutions possess unique properties. This conclusion is known as the black hole uniqueness theorem, and it has far-reaching consequences. Most objects in the universe possess a practically infinite set of individual characteristics. Quasars, for example, are giant cosmic engines. Due to intense friction and high temperatures near their central black hole, they generate colossal energy. Accurately describing and modeling a quasar would require trillions and trillions of numerical parameters. Stars, while appearing simpler, also exhibit enormous diversity and undergo significant changes throughout their lives. From supermassive stars that existed for only a few million years in the early universe to ultra-low-mass cold stars that will persist until its demise, they represent a rich spectrum of possibilities. Even small asteroids, less than a kilometer in size, possess unique features and birthmarks formed over millennia of travel through interplanetary space. However, for black holes, this rule does not apply. The permissible solutions describing black holes are strictly limited and fully determined by just 3 parameters, and consequently 3 numbers. It has been proven that to describe a black hole, one only needs to know its mass, electric charge, and angular momentum, i.e., its rotation speed. No other parameters exist. 3 numbers provide complete information about a black hole. As American physicist John Wheeler famously put it, black holes have no hair. Wheeler, a master of memorable phrases, also popularized the term black hole itself. Every black hole in the universe can be classified by its mass, charge, and spin, and by no other parameters. Beyond the event horizon lies an untold number of ways a black hole can form. How is it that all these diverse initial conditions reduce to just 3 numbers? Allow me to enumerate the ways. When a physicist hears these words, they immediately recall another area of physics, thermodynamics, the science of heat, temperature, and entropy. Look around you. The room you are in is filled with air, a gas with a specific temperature and pressure. We can feel both of these properties. We sense currents of warm or cold air and changes in pressure in our ears during an airplane landing. However, we do not feel the individual atoms that make up this gas. In the gas filling a room or an oven, there is an enormous, practically countless number of molecules colliding with each other. There are so many that we, complex biological creatures, cannot distinguish individual atoms. When we talk about a greenhouse on a hot summer day, we are not asserting that the gas molecules inside it are moving faster. We are simply saying it is hot, even if we vaguely realize that the concept of heat hides a microscopic description in terms of rapidly moving high-energy atoms. The world of physics describes various systems through the lens of a few key parameters. Gases are characterized by their temperature and pressure, while black holes are defined by mass, spin, and charge. However, behind these seemingly simple numbers lies an incredible diversity of internal states, configurations, and potential possibilities. For every physical system, there is a fundamental quantity that serves as a measure of this internal diversity: entropy. It reflects the total number of possible microstates compatible with the system's given macroscopic parameters, such as temperature and pressure for a gas. The more microconfigurations correspond to these parameters, the higher the entropy value. In the case of a gas, entropy reflects the total number of ways molecules can move and interact within the system. This is a colossal number of atomic motion variations for given pressure and temperature values. Interestingly, gas entropy increases with temperature. This result is quite expected and intuitively understandable, given that gas consists of a vast number of tiny molecules in continuous motion. Higher temperatures mean molecules move faster and possess more energy. Considering the myriad directions atoms can move, there are far more ways to move quickly than slowly. In the extreme case, when there is no motion at all, a stationary particle has only one way to remain at rest. However, the question arises, can these thermodynamic concepts, well known from examples like gases and rubber bands, be applied to black holes, some of the most mysterious and seemingly dead objects in the universe? Surprisingly, the answer is yes. Despite the absence of swirling atoms or stretching polymers inside black holes, all thermodynamic concepts remain applicable. Just as we can speak of the temperature or entropy of a gas, we can speak of the same characteristics for a black hole. This idea, which emerged in the early 1970s through the work of Jacob Bekenstein, a graduate student of John Wheeler, and later fully developed by British physicist Stephen Hawking, was a true breakthrough. Wheeler, famous for his "black holes have no hair" phrase, noted during discussions with Bekenstein that when hot tea is mixed with cold tea, the total entropy increases irreversibly. However, if this mixed cup were dropped into a black hole, all traces of mixing would vanish as the black hole would absorb everything, turning it into a homogeneous, unique solution. This paradox made Bekenstein wonder, does mixing hot and cold tea truly increase the total entropy of the universe? But when the tea falls into a black hole, all its entropy disappears without a trace. This seemed impossible and contradicted the second law of thermodynamics, which states that the entropy of a closed system must only increase over time. This law is one of the most fundamental in physics. Arthur Eddington, known for his work on relativity and nuclear fusion, once said, "The law that entropy always increases holds, I think, the supreme position among the laws of nature." If someone points out to you that your favorite theory of the universe is in disagreement with Maxwell's equations, then so much the worse for Maxwell's equations. If it is found to contradict observation, well, these experimentalists do bungle things sometimes. But if your theory is found to be against the second law of thermodynamics, I can give you no hope. There is nothing for it but to collapse in deepest humiliation. This is why Bekenstein hypothesized that just as every cup of tea possesses entropy and the total entropy of two cups increases when they are mixed, the same must be true for a black hole. When a cup of tea falls into a black hole, it simply increases the black hole's total entropy by an amount corresponding to the entropy of that cup of tea. What happens if you throw hot tea into a black hole? This very question led Jacob Bekenstein to an astonishing conclusion. Black holes possess entropy, which came to be known as Bekenstein-Hawking entropy. This discovery was a true sensation, but what did it truly mean? Which object in the universe, a black hole, is the hottest? Since the discovery of the first astrophysical black holes in the 1960s, scientists have found a vast number of such objects. The masses of these cosmic bodies differ significantly. The largest known black holes, such as Phoenix A or TON 618, are approximately 100 billion times more massive than our Sun. These supermassive black holes, located in the centers of active galaxies, can generate colossal energy through their powerful quasar jets. The lightest known black holes, discovered as dark companions to other stars or pulsars, are only a few times more massive than our Sun. Candidates for the lightest black holes include objects orbiting the pulsar PSR J05Phi 4002e or the red giant V1723. Strangely enough, these miniature black holes are billions of times hotter than the distant giants, the supermassive objects that power entire galaxies. Although their temperature is just over 100 millionth of a degree, the term hotter here is quite relative. Thus, black hole temperatures are extremely low, but still not zero. But where does this heat come from? By the early 1970s, Bekenstein and Hawking concluded that black holes must possess entropy. The relentless march of time, dictated by the second law of thermodynamics, continued forward. When particles fall into a black hole, their entropy must be transferred to this object. The total entropy of the universe must increase, and the laws of physics must be obeyed. At least, so it seemed at first glance. However, upon deeper analysis of this picture, Hawking's brilliant mind grasped a problem. Imagine hot gas being absorbed by a black hole. It was believed that the resulting black hole should be cold, dark, and compact, from which nothing could escape. It seemed to be an object with zero temperature. In any other area of physics, when hot and cold objects are mixed, the temperature of the cold object increases. However, in this case, the black hole remained inert, with a temperature of absolute zero. This was the essence of a black hole. Even light could not leave its confines. But then Hawking put forward an astonishing and unexpected idea. Having solidified the notion of black holes as thermodynamic objects with entropy, he proposed that black holes also possess temperature. Not just a mathematical analogy or a gravitational equivalent, but a very real temperature, just like ovens, boiling water, and the weather. The most exotic objects in the universe suddenly became frighteningly familiar. Classical laws of thermodynamics, known since the 19th century, link entropy to temperature. Specifically, they state that an object's temperature is inversely proportional to the rate of change of its entropy with energy. For a gas, when energy is added, the number of its configurations increases. By calculating this precisely, one can determine the gas's temperature. For a black hole, entropy is determined by the area of the event horizon. In the simplest case of the Schwarzschild solution, entropy behaves as the square of the black hole's mass energy. Plugging this relationship into the classical 19th century thermodynamic expression for temperature yields an astonishing result. A black hole must have a temperature, and this temperature is inversely proportional to the black hole's mass energy. Large black holes are cold, and small ones are hot. The temperature of a typical astrophysical black hole in our galaxy, formed from the collapse of a star and having a mass only slightly exceeding that of our Sun, is about 1/1000th of a degree. However, a much smaller and currently hypothetical black hole, formed by compressing, for example, Mount Everest to a point, would have a temperature of hundreds of billions of degrees, significantly hotter than the center of the largest stars. Black holes have a temperature inversely proportional to their mass. This means that the smaller a black hole, the hotter it is, and vice versa. Even the tiniest black hole will be immeasurably hotter than the core of any of the largest stars in the universe. This characteristic indicates that black holes behave counterintuitively. A normal flame, starting hot, cools down as it releases heat until it turns into faint ash, which eventually disappears. Black holes, in contrast, heat up as they lose energy. Initially cold, a black hole becomes increasingly hot until it evaporates in a burst of radiation. This is strange, but typical for black holes. To understand this phenomenon, it's worth starting with the question, why do black holes have a temperature? Heated objects radiate heat. If you put your hand near a fire or a hot oven, you can feel the heat without touching them. Hot precisely means the transfer of heat to a cold object. Upon contact, two bodies exchange energy until they reach an intermediate temperature. However, black holes were believed to emit nothing. They were envisioned as cosmic voids that absorb everything that falls into their gravitational nets, returning nothing in exchange. The very word black in black hole indicates that they absorb light without emitting it. But the discovery of entropy in black holes showed that this is not entirely true. If you could put your hand near a black hole at 1,000 degrees, the sensation would be the same as touching an oven at a similar temperature. Just as your hand feels photons from the oven transferring energy to skin cells, your hand should feel photons from the black hole causing a sensation of warmth. But where do these photons come from? For this to happen, real particles must be emerging from the black hole, not just falling into it. In the 1970s, this seemed absurd and contradicted the very concept of a black hole. So, can particles actually leave a black hole? Surprisingly, the answer is yes. Among Stephen Hawking's many contributions to physics, this result is one of the most significant. The light emitted from a black hole is called Hawking radiation and has a spectrum corresponding to the black hole's temperature. Hawking radiation is theoretically justified and confirmed by various approaches that combine gravity, black holes, and quantum mechanics. To understand this phenomenon, one must turn to Heisenberg's uncertainty principle, which states that in quantum mechanics there is no absolutely stationary vacuum and nothing can be perfectly stabilized. Imagine yourself near the black hole's horizon, but outside of it. Crossing this horizon means falling into the black hole, and your fate would be sealed. Instead, imagine you have a rocket with powerful engines that allow you to hold your position at the boundary of the black hole. The engines run continuously, and you remain outside the horizon. Imagine two beacons on the rocket, one pointed towards the black hole's horizon and the other in the opposite direction. Light from the beacon pointed towards the horizon immediately crosses it and disappears into the black hole's singularity. Light from the other beacon, pointed away, leaves the black hole and travels into deep space. This is how Hawking radiation works. Heisenberg's uncertainty principle states that even the coldest, emptiest vacuum is not truly empty. It possesses intrinsic energy, and one can borrow energy from the vacuum for a short period of time. The more energy you want to borrow, the shorter the time period for which it is possible. In quantum mechanics, a vacuum is not just empty space, but a dynamic environment where energy can be borrowed for short periods. This allows the vacuum to create particle-antiparticle pairs, which, however, must quickly vanish, returning the energy to avoid violating the law of conservation of energy. Such behavior demonstrates the complex nature of the vacuum, where nothing is absolute. Consider the vacuum near a black hole's event horizon, where gravitational pull tends to drag objects inward. In this case, the vacuum has a distinct direction, inward. What happens when energy is borrowed to create a particle-antiparticle pair, or, in the case of photons, a pair of two photons moving in opposite directions? For a fleeting moment, energy can be borrowed to form a pair of photons. In this brief instant, the particles can move, and one of them crosses the event horizon, a one-way portal to the singularity. As a result, the pair of photons can no longer reunite. Similar to a rocket balancing on the edge of an abyss and emitting photons in both directions, the quantum vacuum behaves similarly. One particle flies off to infinity, while the other falls into the black hole. The energy borrowed from the vacuum must now be repaid by the black hole. Ultimately, one photon escapes, carrying away a negligible amount of energy, which is compensated by the black hole losing a tiny fraction of its mass energy. Detailed calculations confirmed Hawking's hypothesis that this process resembles the emission of light from a hot furnace. The spectrum of photons emitted by a black hole corresponds to that of a black body with a temperature determined by Hawking's formula. Thus, Stephen Hawking discovered that black holes are not perfectly black, but this discovery raised new questions. If one waits long enough, a black hole will eventually evaporate completely, and its interior will vanish. Imagine a situation where countless encyclopedias and databases fall into a black hole before its formation. Over time, the black hole evaporates, leaving behind only a gas of particles emanating from where it once was. What happened to all the information it contained? According to Hawking's calculations, the radiation is a featureless thermal spectrum containing no traces of the original information. Where did it go? Can the information be reconstructed from the details of the radiation? This question remained a subject of discussion for 2 decades. In ordinary quantum mechanics, information is not lost. Are black holes an exception? Or does the unusual combination of gravity and quantum mechanics lead to fundamental differences? The answer came from an unexpected source, the fact that a black hole's entropy is proportional to its surface area, not its volume. This was the first hint of a profound idea known as the holographic principle, which has enormous implications for our understanding of the universe. Imagine dropping a book into a black hole, past the accretion disk and radiation waves. The book falls until it reaches the central gravitational singularity at the very heart of the black hole, where any information it carries is utterly destroyed. To understand whether information is destroyed or preserved, one must grasp the nature of this central singularity. What is inside a black hole? Is information preserved in the theory of quantum gravity? If we were to record the details of every photon emitted by a black hole during Hawking radiation, could we, in principle, reconstruct the original information? Is it truly possible to recover information absorbed by a black hole? Most of the concepts discussed earlier, such as the existence and entropy of black holes, as well as Hawking radiation, despite all their appeal, were largely developed by the late 1970s. However, in subsequent years, scientists realized that black hole physics contained far more mysteries, hinting at even deeper and more astonishing truths. In particular, the study of black holes provided the first insights into one of the most striking and unexpected properties of gravity, the holographic principle. It is this principle that offers the most promising approach to understanding what happens to information disappearing into a black hole. To begin, it's worth revisiting Hawking's formula describing black hole entropy. One of its aspects, at first glance, might seem quite mundane, but in reality, it represents the first indication of something revolutionary. A black hole's entropy increases proportionally to the area of its surface, not its volume. Physicists knew that a black hole's mass corresponds to the area of its event horizon, an imaginary geometric surface surrounding a spherically symmetric shell from which nothing can escape. For the simplest Schwarzschild black hole, this horizon area depends solely on the black hole's mass. However, for rotating black holes, the expression for the horizon area is more complex, depending on both mass and rotation speed. But in 1971, Stephen Hawking demonstrated that no matter what happens to a black hole, including complex processes that extract angular momentum from a rotating black hole and slow its rotation, the area of its horizon will only increase. According to the second law of thermodynamics, it is entropy that possesses the property of inexorable increase. Initially, Bekenstein, and then Hawking, concluded that it was the horizon area, not mass, volume, or angular momentum, that behaved as entropy should. When objects fall into a black hole, increasing the amount of information and, consequently, the entropy within it, the black hole's horizon area also increases. When two black holes merge, the horizon area of the resulting black hole exceeds the horizon area of either of its components. Even in complex gravitational maneuvers that allow mass and angular momentum to be extracted from a black hole, the black hole's mass decreases, but its horizon area invariably increases. But why is this surprising? Black holes, as mentioned, in some ways resemble gases. Both are thermodynamic systems possessing temperature and entropy. Like heated gases, hot black holes emit radiation. However, there is an important and subtle difference. The entropy of any object is a measure of the total number of internal configurations it can have. That is, a measure of the number of ways its internal components can be rearranged while keeping external characteristics unchanged. For a gas, entropy increases with its volume. If you imagine a balloon at a certain pressure, then while maintaining that pressure, the larger the balloon's volume, the greater the number of possible internal configurations the gas can have. Imagine dividing the entire volume of gas into many tiny cells, elementary volumes of space. Each of these volumes can be either in an on state, for example, a gas particle is present in that volume, or in an off state when it is not there. This is a simplified representation of a gas, but it provides a clue to understanding the physics of entropy. How many configurations are there in total? Each cell can be either on or off, so there are two options for each cell. For one cell, there are two options. For two cells, 2 multiplied by 2, which is 4 options. For 3 cells, 2 multiplied by 2 and multiplied by 2, which is 8 options. And for 100 cells, we multiply 2 100 times. In general, the total number of configurations is 2 raised to the power of the number of cells. So what distinguishes black holes? For black holes, the Bekenstein-Hawking entropy depends on the area of the event horizon, not the volume. In terms of our model with cells, each of which can be either a 1 or a 0, this formula suggests that for black holes, we can count the number of internal configurations by dividing the horizon area into many small cells, each of which is either in an on or off state, meaning it has a value of 1 or 0. The state of a system can be either on or off, corresponding to values of 1 or 0. Counting the states of a black hole is analogous to counting the states of a gas, but with one crucial difference. The counting is done on the black hole's event horizon, not within its volume. The holographic principle states that the entire physics of a gravitational system is fully encoded on the boundary of that system. The equations of gravity inside the system can be rewritten or transformed into another set of equations, describing a non-gravitational theory that exists only on that boundary. Gravitational systems in three-dimensional space can be equivalent to non-gravitational systems on a two-dimensional boundary. Similarly, gravitational systems in five-dimensional space can be equivalent to non-gravitational systems on a four-dimensional boundary. In general, gravitational systems existing in a certain number of dimensions are equivalent to systems existing in a space one dimension fewer. One of the dimensions in the gravitational theory turns out to be redundant. This concept, known as the anti-de Sitter conformal field theory, ADS-CFT correspondence is one of the deepest ideas in modern theoretical physics, as confirmed by numerous calculations. The key idea is that two separate mathematical theories, a gravitational theory, for example, in 5 dimensions, and a non-gravitational quantum theory in 4 dimensions, are actually identical theories, simply formulated in different languages. This correspondence has been proposed as a way to unify previously incompatible gravity and quantum mechanics, which is one of the main goals of modern physics. Bekenstein-Hawking's expression for black hole entropy was the first hint of this theory. But how does holography help resolve the information paradox? Where does all the information that falls into a black hole disappear? Holography asserts that a gravitational system and its evolution can be described using an alternative non-gravitational language. Consider a gravitational system with an alternative non-gravitational holographic description containing a black hole that forms and evaporates. In the context of gravitational theory, the question arises as to whether information is lost in this process. However, in the alternative, holographic lower-dimensional description, the process of black hole formation and evaporation is described in a non-gravitational language. In this description, it is simply an ordinary quantum mechanical system evolving in an ordinary quantum mechanical way, without any problems related to singularities or event horizons. In such an ordinary quantum system, there is no question of information loss. Information is preserved on the event horizon, i.e., on the lower dimensional boundary. But still, even if we know that information is preserved, where exactly is it located? The most probable answer at present is that it is contained in the details of Hawking radiation. Although the radiation emitted by a black hole can be thought of as blackbody radiation, where all components are uncorrelated with each other, this is not entirely true. Physicists believe that all emitted photons are subtly correlated and entangled with each other, and it is within these correlations that the details of the information that fell into the black hole are hidden. Thus, black holes are truly astonishing objects, challenging our perceptions of information and reality. But what are they made of? Once a black hole is formed, and before it evaporates, can we determine what it actually is? For a gas, the microscopic configuration includes the positions and velocities of all the atoms that make up the gas. What is the analog for black holes? This question has no simple answer, and it seems impossible to test experimentally. To access the interior of a black hole and see what it's made of, our hypothetical rocket, equipped with future technologies, would first have to cross the black hole's event horizon to explore its interior. But having done so, this rocket would never be able to leave the black hole, and therefore any bits of knowledge it might find could never be sent back to the scientists remaining outside. Thus, the interiors of real black holes, light years away and hidden by an event horizon, are currently inaccessible to us, both practically and in principle. Mathematics is capable of more than rocket technology. In situations where conducting experiments is not feasible, the best approach is to perform thought experiments or mathematical calculations of systems. These systems may not exactly correspond to the real world but possess key properties similar to it. Studying such mathematically solvable systems allows for insights into real systems. Are there mathematical models that reflect the physical properties of real black holes, yet possess sufficient symmetry and tractability for calculations? In some cases, the answer is affirmative. In a landmark study conducted in 1995, Andrew Strominger and Qumran Vafa, scientists from Harvard University, examined a simplified model of 5-dimensional black holes within string theory. These black holes are mathematical constructs existing in a world with an extra spatial dimension. They also possess specific properties and symmetries not characteristic of ordinary black holes in our universe. However, for these special black holes, Strominger and Vafa were able to precisely compute and identify the possible internal microstates corresponding to the black hole solution. That is, all the internal contents from which it could be composed. This example utilized extended objects of string theory known as D-branes. By counting all the possible ways they could be assembled, the scientists obtained a result that perfectly matched Hawking's calculation. Despite the calculation being performed for a mathematical universe with additional dimensions and symmetries, it still yielded a concrete result. In this simplified situation, it was possible to precisely understand the entropy formula for a black hole from a microscopic perspective and count all the states that could comprise it. Unfortunately, for real black holes, the answers are still elusive. What is inside objects like Cygnus A or TON 618? We do not yet know their internal microstates or a precise description of their interiors from the perspective of physics at the event horizon. However, concepts like the holographic principle offer hope that in the future we may be able to peer inside these mysterious objects at the intersection of gravity, astrophysics, and quantum mechanics. Thus, almost 3 centuries after their first hypothetical existence, black holes remain among the most enigmatic objects in the universe. Friends, if you enjoyed our content, don't forget to subscribe to the channel. Thank you for watching, and we'll see you in the next video.